No matter where you are in the universe, what your environment is like, or how fast you're going, one thing is constant. Every object must obey the laws of physics. From nature, to mass media, to cooking, and in our case, sports, physics is always in effect, dictating what can and cannot happen. So, for my grade 11 physics summative, I will be looking at the physics in basketball, and specifically the physics of LeBron James. I chose this due to two reasons. One being that I have an undying passion for the sport, with the aforementioned player being my favorite, and two being the fact that basketball is special. The size of the court and the lack of pads or helmets give fans the most intimate experience of a team sport that exists. And because of the different styles that basketball allows for, players develop their own distinct identity through their creativity, flair, and athleticism. Although no player succeeds on their own, the two-way nature of the game gives players an unprecedented amount of control over the flow and outcome of a game. This makes it remarkably intriguing when connecting the things that happen in the sport to the underlying physics behind it. Therefore, I'll be solving 8 distinct physics problems out of 8 distinct plays from LeBron's career to better understand the sport as a whole with the physics perspective in mind.
Iguodala to Curry, back to Iguodala, up for the layup. Oh, blocked by James! LeBron James with a rejection.
For the first problem, I'll be calculating the net mechanical work done by LeBron James when he blocked Andre Iguodala in Game 7 of the 2016 NBA Finals. Nonetheless, an understanding of the concept of mechanical work in physics is fundamentally vital before any calculations can even occur. According to the work-energy principle, the net amount of mechanical work done equals the object's change in energy. In this case, the energy is in the form of gravitational potential energy, the energy possessed by an object due to its position relative to the Earth's surface. This has the formula mgh, or mass times the acceleration due to gravity times the height. Since I am measuring the change in gravitational potential energy, I need to measure the change in height using h subscript I, the initial height, and h subscript f, the final height. The reference level for both heights would be the court. By inspecting the situation, I already know that the initial height must be 0, due to the fact that LeBron starts his motion when he leaves the ground. According to ESPN sports analyst John Dorsey, LeBron's maximum vertical is around 40 inches, or 1.02 meters. Therefore, I will use this value for the final height. As for the mass, the NBA's official statistics website lists LeBron's mass to be 113 kilograms. Lastly, the value for the average acceleration due to gravity is 9.80 meters per second squared down. In order to better understand this situation, I have drawn a system diagram by hand, which states all the known values as well as the unknown value I must solve for. I have also included reference coordinates in order to better comprehend the situation. Now I can begin to solve this problem using full grasp. I already have stated the values of our givens. Note that g would usually have a direction of down. Nevertheless, in this case, work is being solved for, and since work is a scalar quantity, I will leave out both the vector notation as well as the direction. In the analysis, I have used the work-energy principle equation and simplified it to equal mgh subscript f minus mgh subscript I. In our substitution and solving, I subbed in the given values and ended up with the final answer in kilogram meters per second squared. This can be rewritten as J, which stands for the SI unit joules. A final definitive answer of 1,130 joules is achieved. Therefore, to paraphrase, LeBron exerts 1,130 joules or 1.13 kilojoules of mechanical work onto the ground in order to lift himself up to block Andre Iguodala.
Williams trying it again. Different result, but Mo Williams, the smallest guy on the floor, gets the rebound. James jumped up to the roof to make the catch and is fouled. He looked at Mo and said, "Could you get it close for me?"
Oh my goodness, what is this?
Second problem, I will be calculating the initial velocity of LeBron James as he leaves the ground to grab the ball. For this question, we will assume no air resistance and assume he is jumping perfectly in a straight line. Velocity is fundamentally defined as the displacement or change in position of an object divided by the time elapsed. This is a vector quantity and is the basis of all kinematics. When an object undergoes non-uniform motion or accelerated motion, its initial and final velocities are different. In this situation, I already know the final velocity of LeBron must be 0 since he is suspended in the air for a brief moment. I also know that since he is jumping vertically, the acceleration that is acting on him is the downwards acceleration due to Earth's gravity. To find the time he took to jump, I played the video back 5 times and using a stopwatch, calculated the time it took him to start from the ground until he reached his maximum height. I averaged these values out to get delta t, the time elapsed, equal to 0.528 seconds. Using these 3 values, I can use the second kinematics equation and then rearrange it to calculate the initial velocity. I get the equation vector vi, the initial velocity, is equal to vector vf, the final velocity, minus g, the acceleration due to gravity, multiplied by delta t, the time elapsed. Again, I have drawn a system diagram by hand with reference coordinates which helps to better understand the problem. Now I can begin to solve this problem, knowing I have already stated the values of our givens and what variable we are required to solve for. In the analysis, I have used the second kinematics equation. Since the final velocity equals 0, we can just take that out. In our substitution and solving, I subbed in the given values and ended up cancelling out seconds with seconds squared. A final definitive answer of 5.17 meters per second up is achieved. Therefore, to paraphrase, LeBron has an initial velocity of 5.17 meters per second up right as he is leaving the ground to grab the ball.
Wade from behind takes it away. Chalmers, Cole, James! Whoa!
Now, onto the third problem, where again we will assume no air resistance. In this play, I am solving for human horsepower done by LeBron when he dunked over Jason Terry in 2013. Power is defined as a transformation of energy over a period of time. That also means power is the amount of work done over the time elapsed. It has the equation P, or power, equal to W, work over delta T, elapsed time. In this instance, LeBron James transforms kinetic energy into gravitational potential energy over a certain interval of time as he jumps up. Since we know work is a change in energy, we can use the equation from problem 1 and sub it in here, resulting in mgh subscript f minus mgh subscript I all divided by delta t. In this situation, we know the initial height must be 0 since he starts from the ground. As for the final height, I will use the value of 1.02 meters that I calculated earlier. The same goes for the mass of 113 kilograms, and the acceleration due to Earth's gravity of 9.80 meters per second squared down. To calculate the time, I used the same method as in the last problem by playing the video back 5 times using a stopwatch. I averaged these values to get delta t, the time elapsed, equal to 0.730 seconds. Another hand-drawn system diagram with reference coordinates is shown here. Notice that the reference level for the heights is the court. Now, I can begin to solve this problem using full grasp. Again, I have already stated the values of our givens and what is our required variable. This is another situation where I will leave out both the vector notation as well as the direction from the acceleration due to Earth's gravity because I am solving for a scalar quantity. In the analysis, I have mgh subscript f minus mgh subscript I divide delta t. Our substitution and solving, I subbed in the given values and ended up with the final answer in kilograms meters squared per second cubed, which can be rewritten as W. This stands for the SI unit watts. Final definitive answer of 1550 watts is achieved. Nevertheless, watts are more used in electrical power. The power of a human, a better unit to use is horsepower. Therefore, I will convert it by dividing by 745.7 to get an eventual answer of 2.08 horsepower. Therefore, to paraphrase, LeBron James uses 2.08 horsepower, or 1550 watts, to convert his kinetic energy into gravitational potential energy over the elapsed time period.
And then wound up blowing them out with Rack's largest margin of victory. Its offense been impressive early. They made 5 shots in a row before Nelson.
As they try to get more and more competitive going forward. Which of these?
To me, you gotta get a feel for how this fourth quarter as West knocks down the jumper.
George on the steal on a bad pass from Bosch. George goes at Allen and throws it down.
In the fourth problem, I am comparing the gravitational field strength in a game in Orlando where LeBron scored 51 points to a game in Indianapolis where he only scored 7 points. I want to see if the gravitational field strength is different between these two cities and if it gave him any advantage in the 51-point game. Thus, I will calculate his weight in newtons in both cities. Gravitational field strength is defined as the force per unit mass acting on an object when placed in a gravitational field. This force field attracts all other objects placed inside it. The magnitude of Earth's gravitational field strength decreases as an object moves farther from the Earth's center of mass. On average, this value is 9.80 newtons per kilogram down. However, it varies place to place, which is due to two reasons. One is the fact that Earth is made up of mountains, peaks, and valleys, and is therefore very uneven. The second reason has to do with the overall shape of the Earth. Surprisingly enough, the Earth is not a perfect sphere, and is instead an oblate spheroid. This means that the center of the Earth, or the region surrounding the equator, slightly bulge out due to the planet's angular momentum. According to the National Oceanic and Atmospheric Administration, the gravitational field strength in Orlando is 9.79208 newtons per kilogram down. Using that same reference, I found that the gravitational field strength in Indianapolis is 9.80114 newtons per kilogram down, a slight difference. For simplicity's sake, I will use subscript ORL for Orlando and subscript IND for Indianapolis. Note that gravitational field strength is a vector quantity, and both directions here are down. Yet again, I had to hand draw a system diagram here with reference coordinates, but with that, I have also drawn two free body diagrams, or FBDs for short. In the system diagram, I have two major force vectors shown, with vector F subscript g, or the force of gravity, pushing down, and vector F subscript n, or the normal force, pushing up. The normal force is just any reaction force and is always perpendicular to the surface that the object is on. In the two separate free body diagrams, I have the object, which in this case is LeBron himself, drawn as a simple dot, with vectors drawn above and below to represent any forces. According to Newton's first law, any object will remain at rest or stay at a constant velocity if the net force of the object is zero. Since LeBron is at rest in the system diagram, it means that the net force acting on him is zero, which therefore means the force of gravity and the normal force have the same magnitude but opposite directions, in both Indianapolis and Orlando. Now I can begin to solve this problem using full grasp. I will first solve for the gravitational field strength in Orlando, knowing his mass to be 113 kilograms. In the required, I have stated that I am solving for vector F subscript g ORL, or the weight in Orlando. In the analysis, I rearranged the gravitational field strength equation to get vector F subscript g ORL equal to vector g subscript ORL multiplied by m, his mass. In the substitution and solving, I get a final answer of 1106.50504 newtons down as the weight. Note that this answer should only have 3 significant digits, however, since I am using this value again in a further calculation, I need to carry all the digits. After that, I will solve for the weight in Indianapolis. All the steps I did here were the exact same, except for a slightly different value for vector g subscript I and d. The required and analysis are the exact same as the last calculation. In the substitution and solving, I get a final answer of 1107.5388 newtons down, which is slightly higher than the calculation for Orlando. Note, this answer, like the last one, should only have 3 significant digits. Nevertheless, I need to use both values for the next calculation. To find the difference in LeBron's weight between Indianapolis and Orlando, I must find the difference between the two values and subtract them, which comes out to be 1.02 newtons down. In this instance, I will now follow significant digits, since it's a final answer. Therefore, to paraphrase, LeBron weighs 1.02 newtons down heavier in Indianapolis than he does in Orlando, which is due to the fact that Earth's gravitational field strength is different in these two cities. Did this give him an advantage at all? Well, I'll let you decide that.
Pacers folks were telling me before the game, as Barbosa misses that shot, will garner defensive first, second.
In the fifth problem of this video, I will be calculating the force of friction between LeBron's shoes and the average basketball court. Friction is defined as the force that resists the motion of an object in the opposite direction of the movement and tries to slow an object down. This occurs when contact surfaces are sliding past one another and is a result of the electromagnetic attraction between particles. The coefficient of friction is the ratio between the normal force of an object and the force of friction. There are two main types of friction, static and kinetic. In this situation, static friction is in effect between his shoes and the court. Ironically enough, static friction actually helps him move instead of restricting it. This is because without friction, LeBron would just stay in one place moving his feet but not going anywhere. To calculate the maximum force of static friction, I can rearrange the coefficient of static friction equation to equal F subscript S max equal to mu, a Greek letter, subscript S multiplied by F subscript N. Note that forces are vector quantities, however since friction is horizontal and the normal force is vertical, you must leave out the vector notation. Now, according to a study conducted by the University of Iowa, the average coefficient of static friction between running shoes and a gym-like court is around 0.60. I will use this value for mu subscript S. As for the normal force, I can just find his weight in newtons and then flip the direction. A hand-drawn system diagram is shown here to illustrate all of this, with the normal force calculated to be 1107.4 newtons up. Notice that this value should have 3 significant digits, however I am going to carry the digits for a later calculation. I have also drawn an FBD for the shoe to decide. Also notice that the direction of the force of static friction is actually forwards, like I said before. On to solving the problem with full grasp, knowing beforehand that I have clearly stated our givens and the required variable. In the analysis, I have the equation I solved for earlier. In the substitution and solving, I get a final answer for vector F subscript S max, or the maximum force of static friction, to be 660 newtons forward. As you can see here, now I only have 2 significant digits. Therefore, to paraphrase, the force of static friction between LeBron's shoes and the court is around 660 newtons forward.
Some pressure here.
And now the big thing is make sure you do not foul anybody here on the dribble.
It's going to be James.
Sure, here it is. See, it's under
3 seconds to go. Throws up the floater. Good night, Cleveland. That is for you.
Back to kinematics in problem 6, where we will be trying to find the horizontal range of the ball if there was no net to interfere. This problem involves projectile motion, and therefore I will be solving for values both in the vertical and the horizontal axis. For this problem, I will ignore air resistance as negligible. Projectile motion is the motion of an object that moves in response to gravity along a 2-dimensional parabolic trajectory. In an object experiencing projectile motion, its velocity is always in 2 components, vertical and horizontal. It also has constant horizontal velocity and constant vertical acceleration, which is inherently due to Earth's gravity. In this situation, we need to find the hang time before we can find the horizontal range. In order to find the hang time, we need to first find the vertical displacement, initial vertical velocity, and vertical acceleration. We already know that the vertical acceleration due to gravity is 9.80 meters per second squared down. As for the initial velocity, I need to find the muzzle velocity and then break it down into its components. The muzzle velocity, I will assume it is 4.5 meters per second while it is 30 degrees above the horizontal. In order to break it down into its components, I have drawn the vectors here and will use some trigonometry to find the initial horizontal velocity and the initial vertical velocity. V subscript Ix, the initial horizontal velocity, is equal to the muzzle velocity multiplied by the cosine of theta, which in this case is 30 degrees. This comes out to be 3.90 meters per second forward. To find the initial vertical velocity, or V subscript Iy, I must multiply the muzzle velocity by the sine of theta, which again is 30 degrees, which equals 2.25 meters per second up. Note that in the case of components of resultant vectors, no vector notation is used, since the x or y denote if it's vertical or horizontal. To indicate up versus down, or left versus right, I will just use a plus or minus sign, which is all laid out in the reference coordinates. For the vertical displacement, or delta dy, I will factor in LeBron's height of 2.06 meters, the fact that he's jumping, and finally, the fact that he has his arm slightly raised since he's shooting a floater. Thus, I will assume that the vertical displacement of the ball is 3.05 meters down, since it starts that distance above the ground and ends up hitting the ground later. We can now start solving for everything in the vertical plane using full grasp. As you can see in our givens, I dropped the vector notation on all our variables, and in the required, I stated that I am solving for delta t, or hang time. In the analysis, I have used the third kinematics equation, but then rearranged it to equal 0. You'll see why I did that in a minute. In the substitution and solving, I sub in the given values and was left with the quadratic function. Therefore, to solve for the unknown variable, delta t, I must use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. Since it is a quadratic, I end up with 2 roots, or 2 answers. However, one answer is negative. Since time cannot be negative, the positive answer is the only valid one. Thus, the elapsed time for the ball that LeBron shot was 1.05 seconds. Now that I know the hang time, I can solve for everything in the horizontal plane, which will give me the horizontal range. In the givens, I have dropped all vector notation, but I have also stated that a subscript x of the horizontal acceleration equals 0. If there is no acceleration, it means that the final and initial velocities of the ball must be the same, and evidently enough, I have written so as such. In the analysis, I have used the first kinematics equation to solve for delta d subscript x. In the substitution and solving, I have subbed in the given values and had to cancel out seconds with seconds to get a final answer of 4.10 meters forward. Therefore, to paraphrase, the horizontal range of the ball following projectile motion when it left LeBron's hand was 4.10 meters forward. This is obviously assuming that there was no net in place to interfere and that the ball was left to be shot freely.
This is the way the game is going to be played the whole game. So the Cavs have to continue to play it at a pace like this and continue to take the shots they're taking.
14-13, Portland back in front. LeBron turned the corner. Inside! He made Yusuf Nurkic a screensaver. 15-14. The Kevlar bench is going nuts.
LeBron James with a dance to the hoop and throws the hammer.
In the 7th problem, we come back to a topic from Unit 3, and specifically, we come back to the topic of kinetic energy. In this problem, I must calculate LeBron's kinetic energy right before he jumps up to dunk on Yusuf Nurkic. Kinetic energy, or E subscript K, is defined as the energy possessed by moving objects. In this case, LeBron is moving, and therefore he has kinetic energy. It is a scalar quantity measured in joules and has the formula E subscript K equal to m, the mass multiplied by v squared, or the velocity squared, all divided by 2. I already know his mass to be 113 kilograms, which I have used throughout this video. As for his velocity, I will use the basic velocity equation. Therefore, I need to find his displacement and the time it took for his motion. The reason why I don't have to use any special kinematics equation is because he has a constant velocity. As soon as he reaches the 3-point line, he reaches his maximum velocity. That means the time it takes between LeBron reaching the 3-point line and him lifting off from the ground will be delta t. In this case, his velocity at the 3-point line is the same contrasted to his final velocity. With a displacement, I know he starts from the 3-point line and ends at the right corner of the key, which is around 2.50 meters. I will therefore use the previously mentioned value for the time elapsed. I again played the clip back 5 times and averaged my stopwatch values to get delta t equal to 0.630 seconds. Here I have drawn a system diagram by hand of LeBron driving to the basket. I have included reference coordinates to better compartmentalize the situation. Using these 2 given values, I can solve for the average velocity, my required variable. In the analysis, I have the basic velocity equation, and in the substitution and solving, I get a final answer of 3.94 meters per second forward for his velocity. Now, I can finally solve for the kinetic energy using full grasp. I have stated my givens with the mass, or m, being 113 kilograms. As you can see, I have left out the vector notation from the velocity, since kinetic energy is a scalar quantity. In the substitution and solving, I subbed in the given values and got a final answer of 877 joules, rounded to 3 significant digits. Therefore, to paraphrase, LeBron had 877 joules, or 0.877 kilojoules of kinetic energy right before he left the ground to dunk on Yusuf Nurkic.
Kind of defense will the Heat throw at him here in the second half. Here's Leonard, goes back, and LeBron says, I'll take it.
That play. Leonard goes back, and everybody stop.
Finally, we are on to our last problem, where we are going to calculate the net force acting on LeBron when he pushed Myers-Leonard. I will use some of Newton's laws to do this. According to Newton's second law, if the net external force on an object is not 0, the object will accelerate in the direction of the net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. This can be represented by the equation sigma vector F equal to m multiplied by vector A. This law, as well as 2 other laws in physics, were coined by English physicist Isaac Newton when he published his book Philosophiae Naturalis Principia Mathematica in 1687. I already know his mass to be 113 kilograms, the same number I have used repeatedly, and I can use kinematics to find his acceleration when he pushes on Myers-Leonard. By inspecting the situation, I realize that he temporarily stops here, a bit before the 3-point line. Therefore, this will be the start of the observation period, and the velocity here, which would be the initial velocity, would be 0. As for his displacement, he ends around 0.755 meters away, which is what I will use for vector delta D. I again use the same stopwatch method to calculate delta t to be 0.523 seconds. I will therefore use this value to calculate the acceleration. Here is a system diagram, hand-drawn with reference coordinates to understand the situation. There is also an FBD of LeBron drawn to the side listing all the forces acting on him. Remember that since his net force is not 0, he will accelerate in the direction of the net force. Now, I can solve for the acceleration or vector A using full grasp. I have already stated my given values. In the analysis, I use the fourth kinematics equation and rearrange it to be vector A equal to 2 times vector delta D divided by delta T. In the substitution and solving, I get a definite answer of 5.52 meters per second squared forward. However, I must carry digits over to the next calculation, so I will carry 3 extra digits. Finally, I can solve for the net force or sigma vector F with me already having said my givens. In the analysis, I have the equation from Newton's second law. In the substitution and solving, I get an eventual answer in kilograms meters per second squared. However, I already know that this can be converted to the unit newtons. Thus, a definitive answer of 633 newtons forward is achieved. This is rounded to 3 significant digits. Therefore, to paraphrase, the net force acting on LeBron when he pushed Myers-Leonard was 633 newtons forward. That concludes my video, and I hope you learned something today in the realm of physics, as well as the realm of basketball. That being said, basketball is not the only aspect that physics can be applied to. Like I said at the start of the video, physics is literally everywhere. You just can't avoid it, so it's best you understand physics to truly understand the world. Thank you, and have a nice day.
That's all, folks.